and as the last speaker, let me thank Eduardo and all the other organizers for putting on such a wonderful conference. So maybe we should give them a round of applause. And I think it's common that usually the last speaker is a very prominent mathematician, but in this case, I think they chose me so that no one would feel guilty escaping out to the beach on a nice Friday afternoon. But so let me thank the remaining participants for showing up to this last talk. But let me also apologize in advance that a rather frightful and technical object appears, prominently in my title. But I will try to make the talk very accessible. And in fact, one of the main goals of this talk is to prove a result that should make the geometry of general algebraic stacks more friendly. And so let me begin with just discussing some motivation of algebraic stacks. So algebraic stacks are a convenient language, to discuss two things. On one hand, they're very convenient to discuss moduli spaces. As most of us are taught, the most natural object that encapsulates the geometry of a moduli space is a stack, because it not only describes what families of your objects are, but also what automorphisms are. And often you get that your particular moduli problem exists for free as an algebraic stack, and there's a universal family over it. But on the other hand, it's also a convenient language to discuss equivariant geometry. And by this, I mean if you take an algebraic group acting on a variety X, you can form the stack theoretic quotient X mod G. And this exists as an algebraic stack, and the geometry of the stack is as if the action, this quotient behaves as if the action of G on X is free. And one of the philosophies I'd like to espouse in this talk is that using stack theoretic techniques to study these quotient stacks can actually be used to prove new results in equivariant geometry. And I will have a couple of applications of that in my talk. So some of the results I will prove today will be just properties of theorems regarding group actions on varieties. But on the other hand, I do believe anything that you could prove using stacks, you could also prove without. But they just, in many cases, are very convenient language. And you can often get very nice and intuitive proofs using the language of stacks. And even if you're not familiar with even what the concept of an algebraic stack is, I claim that you're at least already familiar with what the geometry of these quotient stacks are. Because their geometry of the quotient stack is modeled precisely on the G equivariant geometry of X. In fact, you can even establish a dictionary between the geometry of a quotient stack and the G equivariant geometry of X. So for instance, a point of the stack, by which I mean just a map from the complex numbers to X. That's what I mean by a point of the stack, and it corresponds on this side to just an orbit. And as stacks contain not just points, but they're automorphism groups, group of X corresponds to the stabilizer. And for this reason, we also just denote the automorphism group of a point as GX. And So a function, a global section of the structure sheaf, is nothing other than a function on X that's invariant under the action of the group. Or to extend this, or a morphism from the stack X to variety Y is the same as just a G invariant morphism from X to Y. And a line bundle L on X is just a line bundle L on the variety with the G action, often called the G linearization. Or in fact, the same works for coherent sheaves. So a coherent sheaf is just a coherent sheaf with the G action. And on the stack, one thinks of a coherent sheaf not just as a varying family of vector spaces, but actually a varying family of representations, because the fiber, the vector space over a point, inherits an action of the stabilizer. So you actually get a family of representations. And now properties of the diagonal correspond to just properties of the group action. So the morphism from G cross X to X cross X, where one component is projection, the other is the group action. And you may have heard, if you've seen some talks on stacks, people pay particular attention to the properties of the diagonal. And the reason is because it encapsulates a lot of the properties of the group action. So for varieties, the diagonal is always just a closed immersion, which is rather boring. But for stacks, the properties of the diagonal contain a lot of information. So for instance, if this is a closed immersion, then this is a closed immersion. So the action is free. And in fact, the stack is then an algebraic space, which is a mild generalization of a scheme. Or if all of the fibers of this morphism, or equivalently this morphism, are just finite and discrete, then your algebraic stack is what's called a Deligne-Mumford stack. All of the stabilizers are just finite. Or another way to say that is that this map is unramified. But in general, in this talk, I'm going to address general algebraic stacks. So I'm going to allow the fibers to be infinite algebraic groups like C star or GLN. And let me just give one more example of this dictionary. Run out of room. But well, I'll write it here. So that if you have a smooth point of a stack, you can discuss the tangent space. So by what I mean, there's risky tangent space. So if you have a point X, I'm just looking for ways to extend the map from the complex numbers to the dual numbers. I'm sure no one can read this, but this is the dual numbers, 2x, modular isomorphisms. And on the right-hand side, this is going to correspond to the normal space to the orbit. So the tangent space of Roman x modular the tangent space of the orbit of x at x. And in fact, any geometric property or most geometric properties of the quotient stack correspond directly to G equivariant properties. So even if you don't know what the definition of an algebraic stack is, you can usually follow talks on algebraic stacks just by converting properties here to properties that you're familiar with. And I've already mentioned that the stack theoretic techniques can be useful in order to prove some results about G equivariant geometry. But it's usually the other direction that's more prominent. In fact, it's the general philosophy is that the geometry of these quotient stacks, which is particularly well understood because it's just the G equivariant geometry, in fact gives you key intuition to study the geometry of general algebraic stacks. And I'm going to, the purpose of this talk is to justify that philosophy by proving a theorem that says essentially every algebraic stack is locally a quotient stack. And yeah, so this is the second part of the talk, which is the main result. So it's not true that every algebraic stack is a quotient stack. There are examples, and often it's common that when you write down a moduli problem, you can easily show that it's represented by an algebraic stack, and maybe it is a quotient stack, but it's often tough to show that. And in fact, the general question of when is an algebraic stack a global quotient stack is an interesting but very hard question. It's related to the global geometry of the stack and the existence of certain vector bundles, as well as to some arithmetic properties, such as the surjectivity of the Brouwer map. So the question I would like to discuss instead is are algebraic stacks locally quotient stacks? And to set up the result is I'm going to, throughout the rest of this talk, I'm going to work over a fixed algebraically closed field of any characteristic. And yeah, so there's two main theorems of this talk. The first is both answering this question. And these theorems that I'm going to announce are due to a work in progress with Jack Hall and David Ridd. And in fact, we have a preprint ready. We haven't posted it on the archive yet, but it is available on my website if you're curious. So the main theorem is let's let X be an algebraic stack of finite type over K. And let's let X be a smooth K point with a smooth and linearly reductive stabilizer. So linearly reductive simply means that all representations are completely reducible. So then the conclusion is there exists an affine scheme, spec A, with an action of the stabilizer, action of Gx, and a fixed point. Together with a diagram and the following diagram. So I'll try to squeeze it in here so I could leave this result up on the board. So we have an affine scheme of finite type over K. And so on one hand, when you take the quotient, this maps to the stack, and it's a tau. But on the other hand, since we have a smooth point of the stack, we'd also like to compare the geometry of X to the action of the stabilizer on this tangent space. And so we also have that this maps a tau to the tangent space in a way that's compatible with their GIT quotients. So if I take the GIT quotients, I get an tau map here, and this diagram is Cartesian. And moreover, well, this should be in a tau neighborhood of my point. And so there's a point, so this point W maps to X. And this map, let's call it F, has the further property that it induces an isomorphism of stabilizer groups at W. So F, sorry for squeezing this here, an isomorphism of stabilizers at Y, at W, sorry. Okay, so let me try to parse this theorem. So the conclusion really is that the local geometry of X is modeled precisely on the action of the stabilizer on this tangent space. Yeah, and for moduli problems, this tangent space is the first order deformation space. So if your stack is the moduli space of curves, this is particularly well understood. It's a finite dimensional vector space that for curves you can write down explicit coordinates for, and you can often, well, explicitly describe the action of the automorphism group of your object on this. And so this is saying that, with these hypotheses, of which I'm missing one, so a key hypothesis, yeah. So X is an algebraic stack of finite type over K with affine stabilizers. Sorry. So it's saying that, yeah, tau locally, every quotient stack is a quotient stack of this form, and this is kind of the nicest quotient stacks of all quotient stacks because it's just an affine monolinearly reductive group. It has, just like affine schemes, it has the property that higher sheaf cohomology vanishes. You have an affine GIT quotient, and so just like affine schemes are the building blocks for general schemes or even algebraic spaces, this result is kind of asserting that these quotient stacks are the building blocks of X. You can make spec A smooth, yes. You can arrange it to be smooth. Yeah, and in fact, yeah, so we have this hypothesis here and this hypothesis here. This isn't, both of these are not necessary. So the second theorem is just a generalization of this to singular points. So a finite type over K and with affine stabilizers. And now let's let X be a K point with linearly reductive stabilizer. So then the conclusion is the same, that there's an tau neighborhood of X such that F, which induces an isomorphism of stabilizer groups at W. So it removes the smoothness hypothesis, but drops the comparison to the action on the first order deformation space. You can arrange it to be. The way I've asserted it, it's not, but you can arrange it to be, yeah. Yeah, so the plan, the outline for this talk is to spend most of the time on applications of these two results to equivariant geometry, and then spend the last 10 minutes going through a proof, at least of the first theorem. So at this point, you might object and say, well, wasn't this known? Of course this is true. This is how I think about algebraic stacks. And in some cases, it was known, but in this generality, it certainly wasn't. Let me just summarize when this was known. So in the first case, for Deligne-Mumford stacks, I think these theorems were known for, at least to the experts for a long time, but they first appeared in a paper by Abramovich and Vistoli. And in fact, it's also true for tame algebraic stacks, which is a term introduced by the same authors together with Olson, Abramovich. Where this is just a mild generalization of Deligne-Mumford stack to characteristic P, where you allow still finite stabilizers, but you allow them to be non-reduced, but still linearly reductive. And that was essentially this theorem here was kind of the main result of a paper where they introduced these tame algebraic stacks. And the third case, so it's also known in the case of where you have a quotient stack of an affine by a linearly reductive. And this is a result of Luna, which I'll return to later. But let me just say that even though I'm saying something stronger here in this theorem, that not only is a tau locally a quotient stack of an affine by a linearly reductive group, but it's actually a quotient stack by the stabilizer. So there's still content in this case, and in fact, all that content is essentially captured in the statement of Luna's tau slice theorem, which I'll state later. And the other case where it was known was the moduli stack of semi-stable curves. So Deligne-Mumford semi-stable curves. So here I'm allowing curves that have rational curves only meeting the rest of the curve in 2 points. And these such curves have a stabilizer that's a torus. And despite how simple this is, this stack is actually quite mysterious. For instance, this stack is provably not a global quotient stack. The diagonal is not even affine. And this was essentially the main result of a paper with Andrew Krush. And the second remark I want to make before getting to applications is these hypotheses are some of these hypotheses are necessary. So there's two things that may bother you here. Is that I'm assuming all stabilizers are affine, and I have this hypothesis that the stabilizer is linearly reductive. And I claim both of these are necessary. And for the experts here, I am not assuming that the diagonal is affine. So the assumption that of affine stabilizers is pointwise. I'm just assuming for every point, the stabilizer is affine. So affine stabilizers. Is necessary. Even around a point where you have an affine stabilizer, you need to require that you have affine stabilizers in a neighborhood. So for instance, this is similar to an example that we saw in the last talk, is that if you take a family of elliptic curves degenerating to a nodal cubic over a one-dimensional base, and I remove this point, then I have a family of group schemes where the central fiber is C star, or the multiplicative group. But in nearby fibers, you have an elliptic curve. And if I let this family, just call it G over A1, and if I then take the classifying stack of this BG over A1. This has the property that, well, this is the origin. Fiber over the origin is a copy of B of C star. But at the generic fiber, you have B of an elliptic curve. And so if we look at this point here, you do have a linearly reductive stabilizer, C star, but there's no way that these theorems can be true. There's no way that you can get an étale map from an affine scheme mod C star to here, because it would imply that that at least there's a finite index subgroup of an elliptic curve that's a subgroup of C star. So these theorems are simply not true. So this does not exist. And a similar example. So at least some reductivity hypothesis is necessary. So let's consider just the additive group, GA, is A1. Now this deforms to a linearly reductive group. So I could, if I look at the plane removing the hyperbola over the line, there's a way to give this total family a group structure so that the central fiber is a copy of GA, but that at all other fibers it's GM. And now if I take the total family of, say, G over A1, then there's no way that the conclusions of the theorems can be true for the classifying stack, again, around this point. Simply because if you have an étale map from a quotient stack by GA, then at nearby points, there has to be subgroups of GA that are finite index in GM. That can't be true. Yeah, so it's, yes, so I do think, yeah, I really, yeah, so I would like to be able to remove linear and say reductive or geometrically reductive, but I'm not sure if that's true. It seems much harder. I'm not even sure if that's true in this case of the spec A by a reductive group, but I think it's an interesting question. Okay, so now let's discuss now applications. So the first application is going to be to Luna's étale slice theorem. And this also serves to motivate the title, which was a Luna étale slice theorem for algebraic stacks. And so let me just recall what this theorem states. So the setup is that you have a linearly reductive group. And you have an affine scheme with the G action. You have, let's just do, let's specialize to the case around a smooth point, let X be a smooth point with a linearly reductive stabilizer. In this case, it's equivalent to saying that the orbit is affine. Yeah, the orbit being affine. But if the orbit is closed, this certainly holds, that the stabilizer is linearly reductive. And now let's set, as before, that this nx is going to denote the normal space to the orbit. So the tangent space of x mod the tangent space of the orbit. And so the conclusion is that there exists a locally closed affine GX invariant subscheme, such that there's an analogous picture to here. So the setup is that. So if I want to consider the stabilizer X on W, but certainly, but I want it to be a tau local with respect to the action of group. So with respect to the action of G. So what I do is form this mixed product, W cross G mod GX, where I'll just write this over here, that this denotes W cross G mod the action of the diagonal action of the stabilizer. And so the claim is that that the induced map from W, from this to X, is a tau, and that you even have this X maps to the normal space. And that all these maps commute with the GIT quotient. It's rather a mouthful, but this is the statement of Luna's Tau slice theorem. And these diagrams are Cartesian. And just one point to, so the picture is that, this is actually saying something geometric, that if you have a group acting on a variety X, and you're around a smooth point, and you look at the orbit, it's saying that the geometry of the action of G on X at this point, and at this point, looks like the action of the normal space to the orbit at X. So the action of and not only just the linear space, there's actually a closed subscheme W which sits inside X, so that the action of the stabilizer in W looks like the action of G on X. And just to connect these two pictures, they're stated quite similarly. Maybe I should just point out that, I mean, as quotient stacks, if I take W cross GX and mod out by G, this is isomorphic to W mod GX. So these two pictures are really identical. That's the statement of Luna's Tau slice theorem. And it's really had remarkable applications to algebraic geometry. And so this is our version for algebraic stacks. And if we apply this theorem to the case of a quotient stack, say of an affine mod G, we can actually recover something stronger, a generalization of this. So the first application I'm going to say is a generalization of this Luna's Tau slice theorem, where we can remove this hypothesis. So this is just an algebraic group. But more importantly, we can remove that it's an affine scheme. So it can be any variety or even any algebraic space. But we do have to sacrifice this condition. It's no longer locally closed, but it's unramified. And in this generality, you may not have a GIT quotient. So we have to remove this. But if there is a GIT quotient, then you do have that. So that's the first application. And I should note that if X is normal, then you can actually arrange this to be a local. If X is a normal scheme, then you can arrange this to be a locally closed subscheme. But in general, it's not possible. You have to allow unramified covers. OK. Oh, this was a theorem. I was not supposed to erase that. So the second application is going to be toward a generalization of Sumihiro's theorem. Well, he has many theorems, but his theorem on torus actions. So Sumihiro proved that that if you have an action, so let T be a torus acting on a normal variety, then there exists a T equivariant affine Zariski cover. This is simply the assertion that around any point of the variety, there's an affine neighborhood that's equivariant with respect to the action of the torus. And this is a kind of a fundamental result that, that's even necessary to establish some of the foundations on toric varieties. But it fails, if the normality condition is dropped. So for instance, if I just consider the nodal, if I consider the nodal cubic, this is somehow always the counterexample with the action of C star. And I look at this point, there's no way you can find a C star affine neighborhood of this point. Because if you delete this point, you get C star. And so any open neighborhood of this that's equivariant with respect to C star is everything, but that's projective. But there is a 2-to-1 étale cover, which is just 2 P1s glued at 2 points. And this is the quotient of the Z2 action, which kind of rotates. And C star acts here. But if I remove, and now if I remove this point, it is affine. And it is an étale cover. No longer finite, but it is an étale cover. So we see that, perhaps there's hope. And we see, that if we drop normality, then perhaps what we'd want to do is change the Zariski to étale. And that is the result I want to announce. So the theorem with Jack Hall and David Ridd is saying that now if X, so suppose it's a quasi-compact algebraic space with an action of a torus, so then there exists a T equivariant étale surjective map from an affine. And so, so if X is a normal variety, then this is actually a weaker statement than Sumihiro's theorem because we get étale rather than Zariski. And this was known in the case that X is quasi-projective, a quasi-projective variety by a somewhat recent paper of Brion. And in fact, we can prove something stronger that we can even. He does have those hypotheses, he addresses this question in a few of his papers, but there's one result in his paper that does not have that hypothesis. He does prove it for. Yes. So yes, right. In Sumihiro's theorem of the linearization of line bundles, that is true. But in his application towards this, he did not have a normality hypothesis. In fact, we could prove something more general, that you can replace this with the Delim-Mumford stack as long as you allow as long as you allow yourself to reparameterize the action of the torus, which is something I don't want to address, but up to after potentially reparameterizing the torus. So as a third application, I just want to apply directly a theorem, well, this is the second theorem without the smoothness hypothesis, to the algebraic stack of all curves. And if you just apply the theorem directly and translate the conclusion of the theorem into geometry of the curves, what it states is as follows. So let's see. You need some assumptions to guarantee that the stabilizer group, the automorphism group, is affine. So let's let it be a connected, reduced curve of genus bigger than 2. And the key hypothesis is that the automorphism group is linearly reductive. The conclusion is that, well, first there exists an action, a finite type affine scheme over K, and an action of the automorphism group on it, together with a family of curves such that there's a point here, say it's called 0, where the fiber is the curve you started with, C, together with an action of the automorphism group on the total family, which restricts to the action on this curve. And moreover, this is a miniversal deformation around this point. And this is just a technical way to say that any other deformation of this curve kind of comes from this family. And so these hypotheses here are just to guarantee that the automorphism group of not only the curve, but any deformation is affine. And so, for instance, I mean, this theorem, if you apply it to, if you take a curve that's a Deligne-Mumford stable curve, then this was, of course, well known. But there are many curves with singularities that may have torus automorphism groups where this is new. And so this was known, and I had proven this in the special case when this was just families of Deligne-Mumford semi-stable curves in a paper with Andrew Krush. Okay, now the next application is going to be towards Bielik-Niki-Brule decomposition. Now, one reason why this theorem has so many applications is because it basically says that the geometry of any algebraic stack with these properties, a tau locally looks like the action of the stabilizer on an affine. And so any property that's a tau local, you immediately reduce to these kind of stacks, which are quite easy to understand. And so, so that's, so the theorem is going to be that Bielik-Niki-Brule decompositions always exist for smooth, proper Deligne-Mumford stacks with a torus action. Yeah, so let X be a smooth, proper Deligne-Mumford stack with a C star action or GM action. And let X be the fixed locus. Let X GM be the union So this denotes the connected components of the fixed locus of this GM action. And then there exists a stratification X with these xi's locally closed. And such that each xi maps to ti as an affine vibration. And if there's any part of my talk that addresses enumerative geometry, it's this, but only in the sense that Bielerniki-Brule decompositions are useful in enumerative geometry. And in particular, so this theorem was proved by Dragos Alper in the special case of stable maps to Pn of degree d. And he proved it, this decomposition, so that he could then prove that all Chow classes were tautological. And he even kind of, in this paper, he also speculated that this theorem always holds for any Deligne-Mumford stack, and also that this theorem always is true. And then in the PhD thesis of a student of Andrew Kresh, John Scourer, he also proved this in this theorem, as well as this theorem, in the case, in a very interesting case of, with additional hypotheses, but at least in this case, he proved it with the additional hypothesis that the stack was both tame and that the coarse moduli space is a scheme, which already covers many examples. Okay. Let me do one final application. And this is going to be kind of representability of certain Hom sheaves. So the setup is as follows. So so G is a linearly reductive group. And X and Y are algebraic spaces of finite type over K with actions of G. And then we suppose we have a picture where as part of the hypothesis, I'm assuming that there's a GIT quotient, which I'll call S, and that this map is flat, and that there's a G invariant map from Y to the GIT quotient of X. And then, the conclusion is that then the S sheaf, which I'm denoting as Hom G S underline X Y, which is the functor from schemes over S to sets that takes a scheme T over S to the set of homomorphisms between the pullback of X to Y, which are G invariant. And the statement is that this is an algebraic space, is represented by an algebraic space of finite type. And now I'm saying this because this theorem, if I apply this in a very special situation, I already recover something interesting. So I'm going to apply. So let's consider, let's let Y just be an algebraic space of finite type over K with a GM action. And now I'm going to define the following functors, or the following sheaves. So y0 is going to be the fixed locus of Hom over the base field of GM from spec k to y. So this is, if you think about what invariant, what this Hom set should be, this is the fixed locus. And now y plus is going to be Hom k GM from A1 to y. And this is sort of the attractor locus. And there's another space which was a little more mysterious, introduced by Drinfeld, is taking the Hom over A1 with respect to GM of A2, A1 cross y, where here GM acts with weights 1 and -1. And so then the theorem that if we just apply this directly, we recover kind of a theorem due to Drinfeld. We recover a quick proof of a theorem that appears in like a long paper or a 40-page paper of Drinfeld on GM actions on algebraic spaces. And the main result is essentially that all these three are algebraic spaces of finite type, or algebraic spaces. And moreover, I mean, and the easier part is that there's a map of functors from y plus to y0 by restricting to the origin. And this is an affine morphism. And somehow y tilde is kind of an interpolation between both the attractor locus and the repeller locus. I mean, this can be viewed as a generalization of the Bielaniki-Bernoulli decomposition to singular spaces. Because yeah. But, Drinfeld's motivation of introducing this space is something that's mysterious to me, but I'm sure he had deeper reasons. Yeah, that's the summary of the applications. And I think, in the last 5 minutes, let me try to sketch a proof of this theorem. And I'm only doing this, and I do realize it's a nice Friday afternoon, and this is the last talk, but I think it's worthwhile to do, not just to show you I could prove something, but really to, I think the ingredients of this proof are really interesting. And often, many of our applications of this theorem are really due to one of the key ingredients in this proof. So let me just tell you. So there's really 4 ingredients. The first is just deformation theory. And the second is going to be kind of a characterization of coherent sheaves on certain quotient stacks. I'll write it more explicitly in a second. And then Tanakian formalism. And then Artin approximation. And just to summarize how that means, the method of the proof is really quite transparent. And I assure you that if you pay attention, you can understand the idea in 5 minutes. It's really that this first step allows you to prove this theorem on a formal level, on an infinitesimal level. These 2 and 3 allow you, so the first step is to go to an infinitesimal level. The second and third allow you to lift in kind of the spirit of Grothendieck's existence theorem to the formal level. And then the final is kind of going from the formal level to the tau level. But let me tell you, it's really these 2 that are the new ingredients to this. And let me say what these are. This is the key proposition. So G is going to be a linearly reductive group acting on an affine. And let's let W be a fixed point. And now the key assumption is that I'm going to assume, so this is this affine is assumed to be Noetherian, but not necessarily finite type. But I'm going to assume that the complete that the invariant ring is complete local, necessarily Noetherian, and so I want to consider coherent sheaves on the quotient stack, as well as on the nilpotent thickenings of this quotient stack at this point. So I'm also going to define Wn to be the nilpotent thickenings. So this is a fixed point with the maximal ideal M inside A. And the theorem is that the coherent sheaves on W are precisely families of coherent sheaves on these nilpotent thickenings. And this result at first surprised me, because if you consider just what it says when you take the action of C star on affine space on AN with the 1, 1, 1 action, it says that to give a C star equivariant sheaf on affine space, it's sufficient just to give families of C star equivariant sheaves just on the nilpotent thickenings of this point in affine space. And somehow, if you just define sheaves in a neighborhood, in a formal neighborhood here, it extends to the entire affine space. And the second, so that this describes part 2, second ingredient. The third ingredient is the Tanakian formalism, which says that coherent sheaves of algebraic stacks kind of recover the algebraic stack. The category of coherent sheaves with the tensor structure is enough to recover the algebraic stack. And let me state it formally as this. This is a result, an unpublished result of Lurie, but the version we need is slightly more general, and that was proved by Hall and Ridd. And it says that, so let's just let X be a Noetherian algebraic stack with affine stabilizers. And let's let Y, W be just an algebraic stack of finite type. Then it says that to give a homomorphism from W to X is the same as giving a homomorphism of tensor functors from the category of coherent sheaves on X to coherent sheaves on W. So that is the natural map that takes a morphism W to X to the pullback on coherent sheaves, that this is an isomorphism of functors, of categories, yeah. And this is, so this is true and it was classical for schemes, but when you go from schemes to algebraic stacks, you need to allow your functors to preserve the tensor structure of the categories. But anyway, let me now summarize now in a few minutes how these ingredients sum up to prove at least the first theorem. So our picture is, on one hand, we have our algebraic stack here. And we're trying to get an Natal chart that looks like the action of the stabilizer on the tangent space. And so we have X, and then let's consider the tangent space mod the stabilizer. And let's just call this T, script T. And it's too much to expect that there to be a map from here to here, but somehow we want to work a tau locally on this and get a map. And so the first step of the deformation theory asserts that, here I have my point x, and here I have my point 0, asserts that the nth nilpotent thickening of the origin in the tangent space is isomorphic to the nth nilpotent thickening of x in x. So at least if I take the nth nilpotent thickening here, at least I have maps going like this. OK. And that's the easy part, to get it on the infinitesimal level. And now, so let's look at the GIT quotient. And let's call that T. And let's complete it at the origin. And take the fiber product. So let's call that this T hat. And here we have Tn sitting inside here. And we have maps like this. So now I'm going to combine these two and 3, to get a map from T hat to x. And so yeah. And this is really miraculous. So I want a map from homomorphism from T to x. But now I use the Tanakian formalism to say that this is the same as a homomorphism, at least a tensor functor, from coherent sheaves on x to coherent sheaves on T. And now I use the fact that this is now a quotient stack of an affine mod, a linearly reductive group, and has a GIT quotient, which is a spectrum of a complete local Noetherian ring. So I can apply this key proposition to conclude that the coherent sheaves on T are the same things of compatible families of coherent sheaves on the nilpotent thickenings. So this is the same as Hom tensor from coherent sheaves on X to families of coherent sheaves on Tn. And now I could take this inverse limit out, and I get and apply Tanakian formalism again to say that this is just a family of maps from Tn to x, which I have. I have that by deformation theory. I've constructed these maps from Tn to x. So the Tanakian formalism and this property give me for free that these maps extend to T hat. And this is really the hard part. And now, since I've taken up too much of your time, I'll just say, once you have this map, then you can apply Artin approximation to a very natural functor to get an étale map. You apply it to a functor over T to then get an étale scheme, an affine scheme, and an étale map to T, such that all of those properties hold. So I'll end there. Thank you.